So it's my pleasure to welcome Adrien Le Boudec from Louvain, and he's going to talk on uniformly recurrent subgroups and lattice embedding.
Okay, thank you very much. In this talk, my goal is to say something about a class of discrete groups, and more precisely to try to understand how this class of discrete groups can embed as lattices in some locally compact groups. So to define this, I need some background. So most of the talk will be to give some background and a survey talk in order to define this class of groups. And eventually, at the end, I will say something related to the title of the talk. Okay, so I should first define uniformly recurrent subgroups. So this would be U or S. So the setting will be the following. So gamma is a countable group. And we will consider the Shapley space of gamma, which is the space of all subgroups of gamma. So we view this as a subset of the set of all the subsets of gamma, and this one is a compact space. By its scalar theorem. And it's not very hard to see that this one is closed in there, so it's in particular also a compact space. So the group gamma acts in the space just by conjugation. And we want to say something about this action. More precisely, we want to understand the closed minimal invariant subsets for this action. So the definition of the cohomology is due to Jasner and Weiss in 2014, maybe. So a uniformly recurrent subgroup, or URS, is a closed invariant and minimal subset of the Shapley space. So minimal means no proper closed invariant subset. Okay. So trivial examples of uniformly recurrent subgroups are normal subgroups because they are fixed by the action, so they are just fixed points. So of course we want to understand uniformly recurrent subgroups different from this one. So one way to obtain a uniformly recurrent subgroup is to have an action, a minimal action on a compact space. So this is Jasner and Weiss. So assume X is a compact space, and gamma acts on X by homomorphism, and the action is minimal. Then we will get a URS from this. So the way to do this is the following. So we have an action on a space, so in particular we have a collection of subgroups, which are just the point stabilizers. We consider all point stabilizers for X in X. So this is not a URS, for example, because this is not closed in general. So we can take the closure in the Shapley space.
So a URS is not an individual subgroup.
It's not a subgroup.
It's a collection of subgroups.
Yeah, exactly.
Okay. Fine.
Then you can say that a subgroup is a URS if it belongs to a URS in this sense. You can also.
Oh, I see.
Okay, so we have a closed invariant subset, and it's not minimal in general, even if the action of gamma on X was minimal. But the statement of the proposition is that this one contains a unique minimal subset. So then contains unique URS. So called stabilizer URS of the action of gamma on X. Okay, let me just explain an example that in general we lose a lot of information on the action by going from the space to the URS. For example, consider the case of the free loop F2 acting on the boundary of its regulatory kilogram. Then this action is definitely not free because any non-trivial element here has two fixed points in this space. But it's not hard to see that this stabilizer URS is trivial. So by the trivial URS, I mean just the singleton, which is the trivial subgroup. So we may very well have trivial URSs starting from non-free actions. This is just to keep in mind. Okay, and although this is not related to the end of the talk, let me mention that the converse of this proposition is also true. This has been proved by Elek for finitely generated groups and Matebon and Sankoff in general, namely that as soon as you have a uniformly recurrent subgroup of gamma, then we can find a compact space X and a minimal action such that by this proposition we obtain the URS we started from. Okay. I will need to recall a few facts about binary theory. So all that I'm going to say is due to Fürstenberg in the 60s. So the word boundary in this talk will always be for the following data. So X is a compact space. And gamma acts on X. So we say that X is a boundary, or gamma boundary, if the action is minimal plus strongly proximal. So this means that as soon as we have a probability measure on X, then we can shrink this measure to a delta measure thanks to elements of gamma. So if you consider the orbit of this probability measure and we take the closure of this, then we ask that this contains a delta measure. Okay, so one important fact in this theory due to Fürstenberg is that as soon as you have a compact convex gamma space, then you can find a boundary inside. And the second fact that I will use later in the talk is that for every countable group gamma, there exists a unique gamma boundary which is maximal in the following sense. So there is a unique space that will be denoted like this for first standard boundary of gamma. So there's a unique space which is a gamma boundary and such that so for every x gamma boundary, there is a continuous gamma equivalent map from the big one to x.
If you can what convex was.
A convex means so a subset of locally convex topological vector space. So this map we ask it to be continuous and equivalent. So it's maximal in the sense that it maps onto any other gamma boundary.
Is it obvious that you have a model group that its chroma boundary is not, or, I mean, what is known there, is that a boundary in this sense or not?
So you're asking about Gromov hyperbolic groups?
Yeah.
Yeah, so if we have a Gromov hyperbolic group and the action on the Gromov boundary is a boundary in this sense.
So what about cat zero? Is that going to be true as well? Or?
Cat zero.
So you have a group acting geometrically in a cat zero space, you look at its boundary, is that boundary going to be
No, because you need minimal.
minimal up?
So
Okay, yeah,
rank
yeah,
one
yeah.
cat zero is okay.
It is okay, okay, it's the minimal issue, all right.
Rank one cat zero is
Okay, so one important property of this space is that point stabilizers for the action, so gamma x in the maximal boundary are amenable. So how do you view this? You consider the space of all means on gamma. This is a convex compact gamma space. So by this, it contains a boundary. And now by definition, by characterizations of amenability, point stabilizers for this one are amenable subgroups. So we have found a boundary with amenable stabilizers. And I claim that this implies that these must be amenable because these must be smaller. If you go to a quotient, then the stabilizer subgroups will become larger. So if we have one with amenable stabilizers, then these will be amenable as well. Okay. So we said at the beginning of the talk that if we had minimal action on a compact space, we had a uniformly recurrent subgroup, and this we have a minimal action on a compact space. So let's consider the URS associated to this action. So definition. So gamma is still a countable group who is denoted by A gamma, the stabilizer URS. Associated to the action of gamma on this space. And so in this particular example, we can actually forget about URSs. In this case, this is the same as the set of stabilizers. So this equality is a result of commentaire and infinity. So you may want to forget about stabilizers URSs and just take as definition this for this. Okay, so what do I mean by amenable uniformly recurrent subgroup? I mean uniformly recurrent subgroups so that all subgroups inside are amenable. So we have seen that this one is amenable and it has the pleasant property that it's larger in some sense than all other amenable uniformly recurrent subgroups. So we need the following definition. So if we have H and K, two uniformly recurrent subgroup of a group gamma, so we'll say that H is smaller than K if we can find H in H and K in K, such that H is a subgroup of K. This is a natural definition, and the fact is that for uniformly recurrent subgroups, this is an order on the space of URSs. This is an exercise to check. Just we play with minimality and okay, so what I said before is that not only this one is amenable, but it's larger than any other amenable URS. So this has been observed in the joint work with equivalence integral. So the proof is very easy. I will show the proof. So we have, so for every amenable URS H, we have H smaller than H. Okay. So what is the proof? We take subgroup H in H, and we know that H is amenable. So it has to fix the probability measure on the first and back boundary of gamma by amenability. So there is this mu on the space that is fixed by H. And now you will use strong proximality. We can shrink this measure to a point. So we know that we have gamma I and X in this space, such that gamma I mu converges to the direct measure of X. And consider, so HI, we consider the conjugation of this element gamma I on H. So this is an element of the URS because the URS is invariant. So by compactness, we may assume that this one converges to some K, which remains beside the URS. And now the claim is that K has to fix X. Why this? Because if you take an element of K, so this convergence means that eventually our single element will be in these subgroups. So eventually we will have to fix this probability measure, which converge to delta X. So we will have to fix X. So this shows this. And by definition, this exactly means that, so we have found a subgroup inside H, which is inside a subgroup inside A gamma. So this means that the US was found. Okay, so for the talk, I will divide the class of groups into two. The groups for which this URS is just a point, and the other one. So we will note by C the class of groups gamma, such that the URS A gamma is just a point. And in this case, one can check that it has to be equal to the amenable radical of gamma. Okay, so my goal later in the talk is to say something about groups outside C, but it's actually more convenient to consider C a
Sorry, could you just tell me what that's read for?
so this is amenable radical of gamma. This is the subgroup generated by all amenable normal subgroups, or the largest amenable normal subgroup of gamma.
So the only URS is one containing all the set of all those subgroups.
The only in this case, for groups in C, the only amenable ones would be inside this one. So you could have different URSs, but they all live inside the Chapeauty space of this one. So take for example an amenable group. It can have uniformly recurrent subgroups, which are not points. But this says that they all live inside this subgroup. Okay, maybe before I forgot something. Before going into this, I should say something. So as I said before, the survey of Fürstenberg goes back to the 60s. And for a very long time, the case of discrete groups has not been given a lot of attention until a few years ago by work of Catholique and Kennedy. We showed that we found a connection between this and the reduced hysteralgebra of the group gamma. So they showed that the URS, so gamma is countable group. The URS A gamma is trivial. It's the same as saying that gamma has a simple reduced hysteralgebra. So I don't consider this as the only motivation to consider this class of groups and these objects. I think they're interesting in themselves, but this is an important motivation. So it's a connection between a problem which priori had nothing to do with this.
So you're assuming that the amenable radical is trivial.
When I mean I gamma trivial, I really mean the trivial URS.
You are not, okay.
Yeah, but by trivial, I really mean
The trivial.
the trivial subgroup. I don't mean a point. Okay, but for this talk, I want to consider groups for which this URS is a point. So what I want to emphasize is that the class C is huge. So we know that many classes of groups belong to C. I will give you a few examples. So example 0 is amenable groups. More interesting examples, linear groups. This is due to Goya, Kazantar, Kazantar, Ozawa. A cylindrical hyperbolic group. So this is a combination of results of Damani, Gardel, Zin. And Voyer, Kalentar, Kanizozawa. The class of branch groups is also in C. And this is branch result with lattice. And there's also work of Kerr and Sagi who show that certain groups, not all, but certain groups acting on K0 cube complexes belong to the class C.
Is this related to uniform exponential growth, or is that paper by Karen Sagi, or is it a different thing?
It's not the same thing. I don't think. Okay, so not only we know many examples in C, but we also, so C is stable by some different properties. So C is stable by taking normal subgroups. It's also stable by taking quotient by an amenable normal subgroup. And it's also stable by extensions. This is so there's no hope to build groups outside C from these pieces, let's say. Okay, so what I want to do for the rest of the talk is to say something about groups outside C. So first, I should give you examples. And these examples come from groups acting on trees. So T will be simply a tree, let's say open finite. And gamma is a group acting on T. So I always assume that there's no finite orbit in the tree or the boundary. And also that there's no proper invariant subtree. I want the direction to be minimal in some sense. Okay, so given a group like this, I will give you a procedure to build new groups, still acting on the tree. So, if we want to have one example in mind, we can think of gamma just being the product of cyclic group of 2 with cyclic group of 3. So very uncomplicated groups. So now, given such a gamma, we will consider a new group, which is the group of automorphisms of the tree T acting not like gamma, but piecewise by gamma. So what do I mean by this? So we consider the automorphisms G of the tree T, such that we are able to find a finite subtree A such that the following holds. So if we consider the complement of A, this is a finite union of subtrees, T1, T2, etc. So if we denote the complement of A as a disjoint union of Ti's, then we want that for each of these pieces, the action is given by an element of gamma. The element of gamma need not be the same in different pieces. So for every I, there exists gamma I in gamma, such that G is equal to gamma I on Ti. So this is for piecewise like gamma. So it's an exercise to check. It's not completely obvious from the definition, but this is indeed a subgroup. Okay, so I wanted to give you examples of groups outside C. So the theorem is the following. So if we make very simple assumptions on gamma, which are assume that vertex stabilizers in gamma are non-trivial and amenable. So for example, finite non-trivial, then the group PW of gamma lies outside C. Okay, let me give you a concrete example of this in the case of a regular tree. So, T is a D regular tree. And we do the following. So for every vertex, we have D edges around, and we color them from 1 to D. We fix the coloring of the edges of the tree like this, such that if we have two neighboring vertices, so around every vertex all colors are different. And we take a permutation group F on the D lattice. So the universal group defined by Berger and Moses is the group U of F, which are automorphisms prescribed by F. So what does this mean? This means that around every vertex, so this one is going to move somewhere else, and we will get a local action around this vertex, which is a permutation of the letters 1D. Then we ask that for all vertices, this local permutation belongs to the permutation group F. So what is the PW of this group? So we want to have this condition, but outside a finite subtree. So this is the same as asking the condition, not for all vertices, but for all but finitely many vertices. So there's no need to make any assumption for this definition, but from the beginning I had only countable groups. So in order this group to be countable, the condition of the permutation group is that F must act freely on the letters 1D. Then this one will be a virtually free group, but this one will be very different. So let me note this group by GF. And we can play a second game, which is to prescribe the action by F for all but finitely many vertices, but also to prescribe the action by some other permutation group at all vertices. So assume you have a bigger F prime containing F. Then you can also do this. We intersect this one with the universal one associated to the bigger permutation group. And this one is also an example of side C. So to motivate the remaining of the talk, let me say a few words about what is known about these groups. First, it's not only countable, but it's always finitely generated. So it's a subgroup of this universal group, which is a closed subgroup of OT. And it's not very hard to check that this one is actually a dense subgroup in there. And finally, we can find some conditions on the permutation groups such that this group is virtually simple. It's never simple, but simple up to finite index. And there are some conditions. We just say some GF1 are virtually simple groups. This ends the example. Okay, so one question I'm interested in is to understand better the class of groups outside C. And more precisely, so given a group gamma, so such that the Furstenberg RS is not a point, and when it's not a point, it's always a Cantor space. So we want to understand how the group gamma can sit inside locally compact groups, and more precisely, what can we say about the locally compact groups containing gamma as a lattice?
What do you mean by lattice? Because we had a lot of appearances of this word, so maybe you just
Okay, so G, so there exists a probability measure invariant on G mod gamma. So gamma is discrete, G is locally compact, and invariant probability measure on G mod gamma. So one particular case I'm interested in is the case of lattices in product of two groups. So to put into context, we call that Berger and Moses have constructed lattices in the product of two trees, which are also finitely generated and actually finitely presented, which are also dense in some universal group U of F, and which are also simple. So the similarities between these two family of groups motivate the question to understand, for example, the locally compact groups that may contain some of these groups as lattices. So before stating the result, I need a few definitions. So the first one is, so we defined earlier strong proximality. And we want to have something stronger. So if we have a group gamma acting on space X, we see that the action is extremely proximal. If, so before we wanted to shrink probability measures, now we want to shrink closed subsets. So if for every C closed subset in X, so we can shrink C to a point in the sense that there exists a point n in X such that for every U neighborhood of X, we know that we have gamma and gamma that will send C inside U. We can make C as small as possible around this point. And so this is something stronger than strongly proximal. So let me give you examples of this. For example, groups acting on trees. If we have gamma acting on T as before, then the action on the set of ends of the tree is extremely proximal. And so extremely proximal actions are also arise for groups as before. As before meant no finite orbit in the tree or in the boundary, and no proper invariance of tree. And so other examples are groups acting on the circle. If we have a minimal action on a group gamma on the circle, and which is not an action by rotation, or not conjugated to an action by rotation, then the action is extremely proximal. So this is due to G's and modules. And just to illustrate the fact that this is strictly stronger than strongly proximal, let me give you another example. SL3Z acting on the projective space. This is strongly proximal, but not extremely proximal. Okay, and we need one last definition, which is, so if we have a uniformly recurrent subgroup H, then the envelope of H is just the subgroup of gamma generated by the subgroup inside. It's a very normal subgroup of gamma. Okay, and so finally, the theorem is that assume you have gamma finitely generated group, such that first we want that the Furstenberg URS of gamma comes from an extremely proximal action. So I didn't define this. This means that there exists a space X on which the action of gamma is minimal and extremely proximal, such that the associated URS is this one. And assume, so we want to say something about gamma. And it's very natural to say something about the envelope of this uniformly recurrent subgroup, because the only assumption so far is on this. So if this URS is too small compared to gamma, there's no chance to say something about the entire gamma. So if we assume, for example, that the envelope has a finite index, then the conclusion is that gamma cannot be a lattice in a product of two groups. In the sense that your gamma is a lattice in a product of G1 times G2, then one factor must be compact. Okay, just to finish, let me say two things. The first one is that, in particular, this theorem applies to the groups GFF prime we saw before, and there are some conditions on the permutation groups F and F prime, and says that so these cannot be lattices in product. And second one is that we can relax both two assumptions here. We can relax first the finite generation assumption, and we can also relax the assumption on the envelope. We still have to say something for the theorem to be true, but finite index is a lot to us. We can ask something much quicker. Okay, I will stop here.
Any questions?
We have concrete case of application.
The motivation was the. Oh, you want to reverse it, or you want?
What was the motivation?
The motivation was the groups GFF prime, which are dense in these locally compact groups. So there's actually not a lattice in OT because the image is dense, but the similarity that I said before with the groups constructed by Berger and Moses more or less motivate the question to understand into which groups these can be lattices. So they cannot be lattices in products by the theorem, but so by another construction you can also view them as lattices somewhere in some different groups. Not products, but they are lattices somewhere.
More questions? Okay, then I have a question. And what about if you have a product of more than two groups, if it's like 3 or more? Can you say anything?
I guess if you have a product of 3, you can view it as a product of 2 and apply this. Right? And
Okay, so you think that there is no kind of constraints anymore? Because on products of 3 trees, there are some problems occurring sometimes. That's why, like by this analogy.
no, you will have the conclusion. So if you have a product of 3 groups, you can view it as a product of 1 and product of 2. And 1 has to be compact. If it's the product of 2, then you're done. And if it's the 1, then you apply it again. And it could be any finite number of groups.
Okay, thank you. So let's thank everyone.